Okay, we can go ahead and get started. So, hello again, everybody. My name is Dylan. I'm an undergraduate student here at Texas A&M, and I've been working with high-performance research computing for a while now. Myself and another student, Levi, have also been teaching these kind of 1-hour primers on topics that that are of a lot of peak interest to our users. So the way we typically do them is we have the attendees vote on what topics they want to hear about next. So the first one was Linux, and then we talked about Terra, and now this is our Ada primer for our other cluster. Let me share my screen again. Once this is over, in the next emails that get sent out, you guys can vote on the next topics. I believe next week has already been chosen. Next week, we're going to be talking about data management on our clusters. And then the weeks after that, I believe are still up in the air. So you could, if you have an idea for a primer or a topic that you really want to hear us talk about, then you could vote on it there in that email that gets sent out, and we can make a little primer about it. So let's go ahead and talk about Ada today. I'm going to close these. And Shayna will be in the chat answering questions. So if you guys have a question that I miss, she will probably not miss it, and I'll be there to answer for you. So this is actually Ada over there in the data center in Teague, which is, if you've ever been to Help Desk Central, it's actually above like 2 floors or three floors above Help Desk Central. Ada's a pretty big cluster. It has 8 login nodes and 792 64 gigabyte compute nodes. So by far, the majority of the nodes have 64 gigabytes of memory. We also have 9 nodes with PHY cards, accelerators on them. So if you have code that can utilize them, they're mostly open most of the time. Then we have 2 kinds of GPU nodes. Excuse me, 3 kinds of GPU nodes. 64 gigabyte K20s, 256 gigabyte K20s, and then 256 gigabyte large memory nodes. And then we also have 4 V100s, the NVIDIA Tesla V100 cards, which are very big and very cool looking. We only have 4 of them, and they're very fast GPUs, and they are kind of popular. I think they have their own special queue. So if you want to use them specifically, you specify so in your job script, which we'll talk about kind of towards the end of the class. But those V100s are actually really cool. And then they actually present like this, so you could get a better look. Okay. Oh, it looks like the topics are already chosen. Sorry, but the next topics, you guys can vote on them. So it looks like data management's up, and then Slurm job scheduling, and then Jupyter Notebooks on Open on Demand. That's going to be a good one. So back to the configuration of Ada. So we have the K20 GPUs, and then we have the V100 GPUs, only a couple of those. Those have 24 cores. And then we have larger memory nodes, 256 gigabyte, of which we have 6. So there's very, very few of them. And then we have some large nodes with 1 terabyte of memory, and then even larger with 2 terabytes of memory. So there's normally always a spot for your job to run on Ada. It can be very flexible, although most people, if you're using GPUs, most people use Terra. So let's move on. There's a question, what's over here? Do you think we could do a Python Dask tutorial for the HPRC short courses? For the short courses are kind of harder to get in than primers. Primers, we could change the topics more, but I'm pretty sure we could do something with the Python tutorial for a primer to talk about packages and stuff. That'd be a good idea. So this is the actual design of how the cluster is laid out. You can see, so when you log in, you land on a login node, and then the login nodes all share a shared file storage system. They also share that system with the compute nodes where the actual work is done. And obviously there's more than 6 compute nodes, there's hundreds of them. On Ada, there's actually 8 login nodes, but I just didn't want to make 8 boxes. So there's eight login nodes. And then the login nodes communicate with the job scheduler, which is a program that is running across all login nodes and all compute nodes and the entire system. The job scheduler is basically what you submit your job to, and then the job scheduler application reads your parameters, so how long you want your job to run, how many resources your job requires, how much memory, how many cores, etc., and stuff like that. And it finds a spot for your job to run, kind of like a puzzle piece, somewhere on the compute nodes, so that your job can run and everybody's job can run whose resources fit with each other. We use the job scheduler because obviously if we didn't use the job scheduler and people just ran their programs and their jobs from the login nodes or even SSH into compute nodes, it would get pretty hectic, and it is a shared resource, so we have to share what is available. And the job scheduler, in our case, LSF, does that for us. Okay. So batch computing on HPRC clusters. So this is just what I talked about right now. So when you're on campus, well, let's start with the batch job. So what is a batch job? A batch job is a script. It's a text file that contains Unix and software commands that a batch manager and batch manager job parameters. So batch manager job parameters are the directives that we send to LSF. And we're going to see some examples later on. And they all start with a capital B sub, B sub. So those are the parameters, which are called directives. And then we also have Unix and software commands, such as like, loading software, launching the software with your input files, and et cetera, stuff like that. So it's just a job file, a job script file, a job submission script, a batch job file. Those are all the same thing, and they're just a text file with commands that we submit to LSF. So if you're on campus, you're connected to the campus network, you SSH into Ada and you land on the login nodes. From the login nodes, you can either create the job script there or upload or create it on your local machine and then upload it to the login nodes on Ada. Then you submit the job script to LSF. LSF reads it, puts your job in a queue, and then eventually when your resources are ready, the queue puts your job onto a compute node somewhere. And then the output files are sent to wherever you specified or wherever you submitted from if you did not specify, which is the case for most people. So if you submit from, let's say, your home directory on a login node, then your output files will be put inside the directory where you submitted from, so your home directory. The process does not change if you're off campus. The only difference is, obviously, if you're off campus, you're connected to the internet, and then from the internet, you're connected to the Tamu VPN, and then like the exact same as if you're on campus. You follow the same steps. So that's how batch computing works here. So accessing Ada. So this is getting annoying over here. We access Ada through SSH. So if you're off campus, like I said, you need to set up and start the virtual private network, the Tamu VPN. If you go to this link right here, u.tamu.edu/VP network, or if you just Google Tamu VPN, you can find out instructions on how to set it up. You can either connect to the web portal, or if you have like the Cisco client, I'm not sure if they still use that. But you have to be connected to the VPN to access any of the resources, to access Ada or Terra, or to log into the portal. Two-factor authentication is enabled. So by now you're probably familiar with two-factor. So whenever you log into Ada, it's gonna prompt you for a duo request. So you're gonna either have to enter the text code that they send you or do the push notification. So how do you actually use SSH? SSH is it's a command line utility, which is available on most Linux machines. It's actually available on all Linux machines, and then all Mac. So I'm on a Mac right now, so my terminal has SSH built into it. If you're on a Windows machine, that's why we suggested MOBA Xterm. Older Windows machines don't have SSH built in. I think the newer ones have a Linux subsystem that you can use, which has access to SSH. But by default, most Windows machines do not. So to solve this problem, there are tons of SSH programs. The one that we prefer the most is MobaXterm. It includes SSH and X11. X11 is the protocol for forwarding graphics, so you could run software remotely. So say you could run MATLAB on Ada and send the graphics of Ada over to your cluster. Or you could use PuTTY. So the two that we suggest are MobaXterm, which is the preferred one, and then PuTTY, which is basically MobaXterm, same exact thing, just very bare bones. It's pretty much just SSH. I think there's even like Telnet built into PuTTY too. So it's a pretty old piece of software. Or you could access the clusters through the portal, which is a web portal for accessing Ada and Terra both. It still uses SSH, but it just goes all through your web browser. So I'm going to show you the portal real quick, just in case you want to go there. So the portals, the URL is portal.hprc.tamil.edu, which I'll put in the chat now. And we had someone say, in the new Windows, does it come with a bash setup? Oh yeah, see there, Keith got it. Yep. I've actually not touched the Windows the Windows Linux subsystem. I've only heard about it. I don't have a Windows machine, so yeah. So this is the portal. So if you have a Windows machine and you don't have MobaXterm and you want to follow along, you can go to the portal here and you could access the clusters, the shell of the clusters through the portal. So here we're talking about Ada. So we'll go right here to Ada, and then you gotta log in with your NetID, password. And then do the Duo thing if it asks for Duo. And then this is what it looks like when you log into the portal. So to access the cluster over here, we'd go to cluster and then shell access. And this is the same thing. It's going to ask for my password, just like as if I would have logged in from my terminal. So this is just an alternative in case you want to follow along through here. I'm going to use my my terminal on my Mac, but it's available. Also really good if you're in a pinch and you just need to log in real quick and do some kind of monitor over there. Do we have a here then install Ubuntu without moving Windows? You can dual boot, so you partition your hard drive, split it in half, and load Linux on one side and keep Windows on the other. It just divides your memory or your storage in two, and I guess your memory too. Well, not your memory, but it divides your storage in two. So you probably want 2 hard drives. But let's continue. So we're talking about accessing Ada. Use MobaXterm if you can. If not, PuTTY is available. If neither of those are available, then you could go to the portal and go to clusters and then shell access. And then just real quick recap on policies. Login sessions idle for 60 minutes will be closed automatically. So if you're logged into the cluster and you're logged into to one of the login nodes and you just kind of forget that you're logged in, after 59 minutes, 59 seconds, your session will just die. Also, processes running longer than 59 minutes and 59 seconds, so 60 minutes on login nodes will be killed automatically. So you're not really supposed to be running any, you can run stuff on the login nodes to test it, to make sure it runs and it doesn't get any errors. And then once you confirm that there are no errors, then you can, you're gonna wanna quit, kill the process and then submit it as a batch job. Because any processes that run longer than 60 minutes will be killed automatically. So if I were to start, let's say like a data transfer, let's say I'm transferring like a terabyte or so of data, and the transfer takes longer than an hour, the process would die. So for that specific case, file transfers, there's a specific login node. Well, they're not really login nodes, they're fast transfer nodes that you're supposed to log into where the 60-minute process does not apply. So you can make long data transfers like that. We'll cover that next week in data management on our clusters. There's a plug for next week's class. So any process running longer for the 60 minutes will be killed. Just a heads up, we've had some people who email us and say, how come my stuff died on the login node after, an hour? And that's why. And then please don't use no more than 8 cores on the login nodes. So I think on the slide that kind of had the cluster summary, it mentioned that some nodes have more cores than others. The login nodes have 20 cores and I believe 256 gigabytes of memory. I believe all 8 of them do. Not 100% sure on that. Our wiki has the definitive answer, but the idea is there's 20 cores on each login node, and if one person uses all 20 cores, then it could clog up the node and slow it down for everybody else. So that's why we keep this policy in place. This policy obviously does not apply when you're running on the compute nodes. So obviously you can do more work than with just 8 cores. On the compute nodes though, on the login nodes, they're specifically for logging in and kind of debugging your code. So try not to run your stuff there. That'll probably make more sense later on when we talk about what jobs look like and stuff. This is what Duo two-factor looks like on the cluster. So you already know about all this. This has been around for a while, since the 4th of November. We have a wiki page on it. So if you're having trouble with Duo, if you're having trouble today, put it in the chat. If you're having trouble later on, we do have a wiki page which kind of goes over using Duo with some of our software that we use a whole lot. So WinSCP and MOBA Xterm and stuff like that. This is how it'll look in this corner right here. This is what MOBA Xterm and actually all SSH programs look like when you SSH in. So you see, you give the SSH command. So you're connecting to Ada, and then you get this nice little warning message that says you're connecting to a secured system, blah, blah, blah. And then it asks for your password, and then you have to authenticate with Duo, just like this. So download the app, use the Duo push. It's a lot easier that way. What's the maximum time limit for the online portal? So the online portal, if you're connected to a login node, it's going to be 60 minutes. That process applies there. If you're using the portal, I believe the longest you can schedule a job for through the portal is 24 hours, I believe. So I don't want to go into the portal too much because that can be a whole primer of itself. But basically the idea is if you're on the login nodes, you're going to be limited to 60 minutes of time there. So actually you can be logged in for longer. It's just if you're idle for 60 minutes. So if I just forget that I'm there and I don't enter anything into the terminal for 60 minutes, it's gonna kick me off. It's just gonna kill my connection. Or if I have one process running for 60 minutes, then it's gonna kill that as well. So you could log in as long as you want. It's just how long you're running stuff for, you know. I hope that answers your question. If not, you can clarify a little bit. Yeah, so that's Duo on here. And oh, actually we have our first pop quiz. So we're gonna have a poll pop up here in a second. Which of the following is not an HPRC cluster? Is it A, Ada, B, Bozo, C, Curry, or D, Terra? Y'all are a smart group. Bozo. What kind of name is that? Perfect. Yeah, it's Bozo. So Ada, Terra, and Curry are our 3 clusters. Curry is kind of attached to Ada, so it shares some of the same file systems and stuff. I don't think we have a picture of Curry, but kind of looks like Ada. And then Terra is the one that we talked about last week, and it's over there in the corner of Teague. Ada is kind of the impressive looking one because it's really large, so it looks nice. Bozo, yeah. Okay, so file systems and user directories. So I hinted at it before, that there's, if you remember from, oops, sorry, this slide right here, there's a shared file storage system. So all the login nodes and all the compute nodes have access to the shared file system, file storage. So you can put files that you're going to work with there, and the compute nodes can see it, and the login nodes can see it. So specifically, on Ada, there's 3 different file systems, which you're going to want to imagine as 3 separate hard drives. The first is home user, and if you're unfamiliar with Linux kind of nomenclature stuff, this $sign and then capital user, this is a variable. So home user would be, in my case, home and then / Dylan, DYLAN. So it's going to be home / your net ID. So in your home directory, the environment variable is home, and you're given a limit. And there's 2 kinds of limits on each file system. First, there's a space limit. So it's how much actual space the files are taking up, measured in gigabytes in our case right here. And then there's file limits. So how many files are actually there? The file limit quota kind of comes into play if you're making a lot of virtual environments, or if you're dealing with data sets that are large, that have large amounts of small files. In those cases, most of the time you can come to us, send us an email, and we can increase these limits for you, with the exception of the home directory. So in our home, we never increase the home directory because I believe because it's backed up, I believe, nightly. And because it's backed up for each user, we have to limit it to 10 gigs or 10,000 files. So that's kind of the one policy that we never ever change is your home is going to be 10 gigs, 10,000 files, and there's not much we could do about it because we only have so much money to purchase so much storage. And if we start increasing it too much, then eventually we won't be able to do anything on the cluster because there'll be no more space. So what you're supposed to put in your home directory, your important stuff that you really, really don't want to lose. And you really shouldn't be doing too much processing there. You should be doing your processing and keeping your larger files, your data sets and stuff like that inside your Scratch directory. Your Scratch directory is found at Scratch user and then your net ID. And the default limit for Scratch, this is actually incorrect. The default limit is 1 terabyte or 250,000 files. 50,000 is kind of small. So 250,000. So there you should be putting your larger files for ongoing computations. It's important to remember that Scratch is not intended to be a long-term storage area. That's what tiered is for, your archive. So your Scratch think of it as the scratch paper where you do all your work. That's kind of where you put all your important stuff that you're working with currently. Your really important stuff like your results and stuff like that will probably go in your home directory. The work that you're working on currently will be in your Scratch directory. And then lastly, on Ada, we have the tiered file system, which we call the archive. So on tiered, you have a lot more space. You have 10 terabytes and then 250,000. And it's intended to hold all the data that's not frequently used. So you might ask, well, if I have more space in tiered, why not put my files in tiered and then just work with them from there? And the answer to that is that the login nodes cannot see tiered. The login nodes the compute nodes cannot see tiered. The compute nodes can only see home and Scratch. So if you put your data set inside of tiered and then point to it in your job script, when your job script executes on a compute node, you're going to get a nice little message that says file not found, tiered user Dylan not found. It doesn't know what that is. So tiered's an older file system that we keep around for archiving stuff. So that's why you have a ton of space there. And we encourage people to, as they work with their data on Scratch or even in their home, and they're done with their data and they're not going to need to touch it for a while, move it over to tiered, so you have more space in your Scratch directory. Because we do, believe it or not, we do fill up or get close to filling up, and then we kind of scramble to clean as much space as possible while not forcing people to remove hundreds of gigabytes of data off our system. So be a good compute citizen, and if you're not using your space in Scratch, move it over to tiered. And again, tiered is only on Ada and Curie, not viewable from the compute nodes. If you need an increased size in Scratch or tiered, either your space or your files, you can send us an email, and we will always be happy to try to accommodate reasonable requests. If you're asking for 50 terabytes of Scratch, you might be waiting for a long time, but we do try our best to accommodate. This just says we only increase Scratch and tiered. Like I said, we don't increase home. Tiered and home are home is backed up nightly, I believe. Tiered, I'm not sure if tiered is backed up. Tiered is an older like tape system, I think. I forget the actual storage that it's on. I know that home is backed up nightly, but it's backed up nightly, but it's not an easy case to go in there and restore from backups. So it should be like it should be your safety net, not your undo button. That's how it was described to me a while back. Your safety net, as in you just deleted all your data and it's a really bad deal. You can probably come to us. We could find your home directory from a couple days ago. But if you delete a file and you come ask for it, you might be waiting for a while, yeah, because it can be hard to go and, because again, there's thousands of users, so going in there and getting all that data for thousands of users is not trivial. Oh, last thing, if you need a group directory, so you're working in a group, don't just make your directories public. Come to us. We can set up a special directory for you guys, and then dole out the permissions as needed. Don't put your directories to open for everybody. That's kind of just bad practice. People can mess with your stuff. And you can view these quotas on Ada by typing in show quota. So actually, I'm going to log into Ada right now. So I'm going to open my terminal, and I'm going to increase the font size a whole bunch, and go like this so I could see it. Okay, so from my terminal, I'm going to say SSH because that's what we're doing, and then Dylan at ada.tamu.edu. And then I get that this little prompt that says this is a secured system, all that stuff. And I'm gonna log in with my NetID password. You should have an account if you're here, probably. That's why you want to come to an Ada class. So you log in with your NetID password, and then it tells me, it's prompting me for Duo. I'm gonna say, send me a push notification. And then I'm gonna approve the notification, and now I'm here. So this is what it looks like when you log in. Right off the bat, we're given the message of the day. So all this stuff up here is the message of the day that gets printed. This is our nice little COVID-19 response thing. And then if you want to read the stuff again, you could just type MOTD, message of the day. And then right after the message of the day, you're given your quota. So right here, this is what we're looking at. Your current disk quotas are, and it shows us our quotas for home, Scratch, and tiered. So here's the file usage limit, and then the disk space limit, and the file usage limit, and then the total limit that you have. If you want to view this again, the command is show quota, like it says right there. It prints out that limit. So if you're submitting jobs on Ada, or even Terra for that matter, and you're getting some errors in your job script that in your job output that you're unfamiliar with or that you can't seem to track down, a lot of times what it is your job is creating files, maybe even temporary files, in a directory that's full. So like right now I'm using 4,900 files out of my 10, so about 50% of my home. If this was any higher, sometimes it can cause an issue because the Ada won't let you write any more files, which will give an error, and then the job scheduler prints that error, and sometimes the error comes out weird and we don't really know where it came from. We start assuming that the error came from your job, but this is a place where errors seem to happen pretty commonly. Okay, software. So software on Ada and Terra. For full instructions on the software on Ada, we have a wiki page, and basically software is organized into modules. So we have a whole lot of software on the clusters, and then we have a whole lot of different versions of the same software. So in order to organize all that, we use a module system. It's actually called LMOD, but it's accessed through the word module on Ada and Terra. So the way it works is you call module, in this case. So install applications are available as modules, which are available to everyone, except for restricted modules. So if you have a software that is license restricted, that you want to use, first thing, you have to get permission from whoever owns the license on our cluster. That typically starts with an email to us, and then we can connect you with them, or we could you can talk to them and have them email us, or we add you to the restricted software group for there. But this is how you use the module system. Over here on Terra, or on Ada, I'm gonna Control L, clear my screen, and I'm gonna say module list. So module list lists any modules that you have loaded. In this case, I just logged in right now, so I don't have any loaded at all. So I want to load MATLAB, but I'm not sure which versions of MATLAB we have. So I'm going to say module spider MATLAB. The spider command here is the search. So module spider MATLAB. Sometimes the module spider search can be case sensitive. Sometimes it can be case insensitive. There's a couple corner cases where it gets funky, but most of the time, case insensitive works fine. Do we have a question over here? Oh, why should loading modules in Bash be avoided? So that is referring to the sign here. Avoid loading modules in your .bashrc. So this actually right here is a file. So the squiggly line means your home. So it's saying in your home /netid /bashrc. So in your home directory, there's a file, text file called your bashrc. It's a hidden file because it starts with a period, and the bashrc contains instructions for the shell to initialize your shell environment. So what this line is saying is saying inside your shell configuration file, do not load modules because it can cause issues. So basically what would happen if you put a module load inside your bashrc is every time you logged into Ada, your bashrc gets sourced. So the environment gets created from your bashrc file. And if you have, like, let's say module load MATLAB in there, every time you log in, you're gonna automatically load MATLAB. And the idea that's wrong with that is that some modules are incompatible with other modules, or they just don't play well together, because there's thousands of modules. So making all of them compatible with each other is impossible. So if you forget that you've loaded a module in your bashrc and you go on to load another incompatible module, that in a similar way to filling up your home directory or something like that can cause errors that are hard to diagnose. And it's hard to track them back. That's why we say avoid loading modules in your bashrc. People still do it, but avoid it if you can. So back to my terminal over here, the module spider command can take a while because it has to look at all the modules, and there's thousands of them. So I used it. It took a while to search, and now I'm gonna use my keyboard to go up and down the arrow keys, and I'm gonna scroll till I see MATLAB right here. Okay, MATLAB. These are all the versions of MATLAB. So you get the name of the module, you get a description of the software, a numerical computing environment. It's great, and then we see all the versions. So we have versions of MATLAB all the way from 2014A. So I want the latest version. So I'm gonna say 2019A. I'm gonna go ahead and Command C to copy this, and then to get my prompt back, I'm gonna hit Q on my keyboard. Hit Q, and now I have my prompt, and I can type here. So now that I searched for MATLAB, and I found the one that I wanted, I'm gonna say module load to load this version. So Oops, sorry, I hit caps lock on accident. Module load this time, and then you paste in the name of the version that you want, and you hit enter, and it's gonna go ahead and load it. And while it's loading, we have another question. What is MATLAB 999? So this is a super advanced version of MATLAB. No, I'm just kidding. It's a, I believe that is the version we use. So in the past, we used to not require you to specify a version. In other words, I could just say module load MATLAB, and it would load some version. I'm not sure which version it would load. So this one right here is, I think if you just type module load MATLAB, it loads this one, and then it tells you, hey, you need to specify a version. That's why it's there. It's kind of like a check in the LMOD system that we have, because when we used to not require people to specify which version, people didn't know what version they were using, and then when they had issues, it was hard for us to help them because we didn't know what version they're using. They didn't know what version they're using, so we didn't know what errors they were getting or how to troubleshoot those errors for them. That's why we required it. That was a change a couple years back, I think. MATLAB 999, yeah. Yeah. So okay, now that I've loaded 2019A, I have access to MATLAB. So I can now just say MATLAB like this, and it's gonna start a MATLAB client, starting MATLAB from host login 5. I don't think I specified graphics, so in this case, oh, is it gonna do it? Okay, well, it's gonna run graphics then. MATLAB, so MATLAB has both a graphical client and a command line interface client. If you don't have graphics available, it'll just run the command line interface. I guess right now it's trying to run the graphics, but I don't know if it's working. I don't think it's working. It shouldn't work, but that's the gist of it. I'm gonna Control-C to kill this process, or I'm not. MATLAB just has a mind of its own now. Okay, we'll let it do its thing. So that's how you load software. So before we loaded MATLAB, if I would have said MATLAB, it says you'll get a bash error that says command not found. It doesn't know what MATLAB is. So what basically the module system does is it adds MATLAB 2019A to your path in a really kind of easy and intuitive, once you get to use it a whole lot. It really becomes intuitive. I can't Control-C out of this. Okay, we're just gonna do a sorry about that. It becomes intuitive once you use it for a little while, and it's a lot better than just having thousands of the same version of software, because people do need specific versions. So okay, now we're back in here. Great. So I'm gonna type module list again. Oops. That worked even though I misspelled list. That's interesting. And now instead of telling me that I have no software or modules loaded, it's telling me I have one. I've got MATLAB 2019A. So to remove this module now, let's say I want to use a different version of MATLAB. You say module purge. Module purge removes all modules. So those are the, and then module list again. No modules loaded. Those are the important module commands to take away. Module list, module spider, module load, and then module purge. So list shows you all the ones that you have loaded. Spider searches all the available modules. Load obviously loads it, and then purge removes it from your system. So every time you log in, your modules are, when the system works correctly, which it does like 90% of the time. Control-Z, is that like it's like a MATLAB thing. Every time you log out, your modules are gone. So every time you log in, you'll have to load again. So it's good practice to remember to you log in, you do some work. Once you're done, you module purge. You close your software first off. So you close MATLAB, save your work, and then module purge, and then log out. That's best practice, but sometimes we forget to turn the lights off when we leave. That's fine. But yeah, that's basically the module system. Every time you log in, you're gonna have to do that again. Modules and tool chains. Tool chains are basically what we call compiler groups. So tool chains contain compilers, and then sometimes like math libraries and stuff. This is what tool chains look like on our cluster. So we have the Intel tool chain with the IO MKL, the math kernel library, the free and open source tool chain, and then the GNU compiler collection. So these basically are just collections of compilers. So if you need Intel compilers, you'd load the Intel ones, the Intel toolchain. If you wanted to just use the basic GCC compilers, you'd load the GCC one. If this sounds really crazy to you, then and it doesn't really matter what compilers you use. I think by default, obviously we we have available the GCC toolchain, so you could use like G++ or G4trans, stuff like that. But these are there if you need a specific version of a compiler to work with your stuff. And this also is because when we build software like Top Hat over here, we obviously have to build it with compilers. So on our system, you're going to see some MATLAB doesn't really have that because it's compiled in a different way. But these open source softwares right here, what we do is we say, in this case, we have the name of the software, and then slash, and then the version of the software. So this is Top Hat version 2.1.1, and then a dash, and then the tool chain that it was built with. So these are the compilers that we use to build it, and then anything else that comes with it. So in this case, this one came with Python 2.7.12. So the reason we do this, and we're highlighting this right here, is because in this scenario right here, this person's loading 3 modules, but they're loading 3 modules that are built with 3 different tool chains. This is a free and open source tool chain. This is the Intel 2017 tool chain, and this is the Intel 2015 tool chain. So if you're loading multiple software that's built with compilers, you'll know it because it has a longer name than just MATLAB 2019. It would have, FOSS 2016 right here. It's this dash. This is the key right here. This dash is the key that says this is what it was built with. You want to make sure that these match. So to solve this, you would just go and load this module with the Intel 2017A, and then cufflinks with the Intel 2017A. And then once all the tool chains match, you'll be good. In this case, if you tried to load this, you might get an error. Sometimes the LMOD system catches it and it says, hey, you're loading different tool chains, or you're loading different compilers. You probably shouldn't do that. But we shouldn't rely on the system to catch our errors all the time, because sometimes the system won't, and then yeah, the errors can be hard and heartbreaking to spend lots of time debugging. I know from experience. So be careful with the tool chains. Just make sure that they match. Okay, consumable computing resources. Basically, there are 2. You've got SUs, and then you've got licenses. So let's start with job files. In job files, you specify some resources. You specify how many cores, you specify how much memory you're going to use, you specify how long the job's going to run for, and then you specify whether or not you're going to use a GPU. The first 3, cores, memory, and wall time, those go into calculating your SUs. So your SUs are the currency that you use when you submit jobs. If you're a student like me, when you apply for an account, you apply for a basic account and you're given 5,000 SUs. That happens once per year, starting in August, I think, August 1st. It's August or September, it's one of the 2. So at the start of the fall, basically, that's the fiscal year for us. So you're given an allocation with 5,000 SUs. If you need more than that, you go to your professor and your professor applies for a startup account. The startup accounts can have up to 200,000 SUs. On the application, your professor lists you as a researcher and then can sub-allocate SUs from his 200,000 down to your account. That's how SUs work. The other consumable resource are licenses. Licenses are shared. There we go. Fiscal year starts in September. Yeah. Users can apply and all that always trips me up. Okay, thank you, Keith. The other resources are licenses. Licenses are shared, so you know, they don't you don't have to worry about them expiring. That's something for us to worry about. But there's only a set amount of them. So we have this neat little tool called license status that you can use, license status, and we could say -A. -A is just going to show us all the licenses on the available. There's a whole bunch of them. Let's just go right here. Let's find one that I can pronounce. Okay, some LS Dyno ones. So there are 2,000 licenses. There's 176 in use and 1,824 available. If the number available is 0, or if the number available is less than the number that your job requires, your job will pend. So when you submit it to the job scheduler, the job scheduler checks to see if it has the required amount of licenses available. If not, your job's not going to die. It's just going to sit there waiting. So the one that we kind of see be used the most was ANSYS. We used to only have a few ANSYS licenses, like 50. I think now we have some more. But I think now we're limited by our MATLAB licenses, I think, because of the whole MATLAB license fiasco with A&M. But the short of it is, if your job needs if your software needs licenses and they're not available, you're just gonna have to wait. Sometimes it can be a headache, I know, but we do try to kind of police it as much as we can while being fair, because it is a first come first serve thing. There's no way to email us and reserve licenses for next week or something like that. You just gotta play your cards right and submit your job. Submit late at night, and maybe the licenses will be available. For the most part, there's always plenty of licenses available, with the exception being like around finals time. A lot of licenses start getting taken up because people are trying to finish up their stuff real quick. But that is the tool for looking at licenses. It's license_status. If you just type in LIC and then hit tab, it'll probably finish for you. -A shows all the licenses. -S shows specific licenses for a software, and then -H for help. The one I did not show you was my project. My project is for SUs. So if I want to check how many SUs I have in my my HPRC bank account, so to speak, the command is my project -L. So here's the command, my project -L, and here's the output. List of Dylan's project accounts. I've only got one right now for fiscal year 20. It's my default account. I was given 5,000. I've used 113, and I've got 4,000 and some left over. And then it lists my my PI that I had put on my application. Okay. Computing environment. I kind of talked about this already. This is the software. This is the takeaway here. The software, and then / the version name, the tool chain, and then any additional add-ons that we had. In this case, it's a Python version that was built with. I don't think we need to talk about anything else from here. The path is there. LD library path is for libraries. So these are, again, variables. So the $ in all capitals implies it's a variable. In this case, it implies it's an environment variable. So these are set when you log in, and then you can add to them and stuff. LD library path is especially useful for computing and batch computing with LSF. In case you want to really make sure that your environment gets copied, you can export this variable inside your job script. LSF kind of does a good job of copying the environment to begin with, so you shouldn't need to do that, but it is available. Yeah, so that's the takeaway from that slide. Batch queues. So job submissions are auto-assigned to batch queues based on the resources requested. Again, resources being the number of cores, and how much wall time. The wall time is just how long your job's going to run. Some jobs can be directly submitted to a queue. So for instance, if you know that your job needs a lot of memory, and I mean a lot of memory, like 1 terabyte or 2 terabyte amounts of memory, you can add this line right here. This is a directive, a B sub that I was talking about earlier. And this tells LSF, I want you to put me in the extra large queue. So it's kind of self-explanatory. You're saying hashtag B sub -Q extra large. The full list of directives can be found on our wiki. We're going to go over some important ones here in a second. But specifically about queues, there's a whole lot of queues on Ada. At the very top, we have the staff queue, the special queue, and the extra large queue. The special queue is for special jobs. So if you're working on something that has very special requirements that won't fit that otherwise wouldn't fit on the regular queues, we could talk to us and we could try to work out a way that we could get your job to run. Like I said, we try to be really accommodating. The staff queue is it's the queue that we use occasionally when we need to test stuff. Extra large queue is for the large terabyte nodes. The VNC is for the portal and stuff. And then you see these other ones right here, like single node short, multi-node short. Those are for, those describe how many nodes you're using first off, and then how long your job will take to run, so the wall time. So your wall time typically determines your queue. You really shouldn't have to worry about that. You just submit your job and then let the job scheduler, LSF, sort all this out. The only time you'd really use this is if you're submitting a job that's pending for a long time and you really want to get down into the weeds and figure out how to get your job to run. Then you might want to break out the puzzle pieces and try and fit it into one of these, or if you want to use the V100 queue, that's another special queue. So similarly to using the extra large queue, you specify, hey, I want this to go to the V100 queue, and then your job would run on a node with the V100s attached to it. This is what a job file looks like. So it's a text file again. At the very top, we have the necessary job specifications. These are necessary for your job to run. So if you're missing one of these, LSF will probably get mad at you when you try to submit it. These are the top lines copy the environment, so it sets the shell. In this case, we're using bash. -J sets the job name. -W says I want this to run for 2 hours, and this is not limited to just hours. I think it can go days, hours, minutes, seconds even probably. And then right here, -N specifies how many cores. And then we have two -R values right here. This is -R span p-tile. So I kind of refer to this as the p-tile value. The p-tile value requests cores per node. So these two are very important. We say 1 core per node. So that specifies how many nodes we're going to use. Obviously, we don't request nodes specifically. We request cores and then divide the cores by cores per node. That gives us how many nodes we're using. And then the second -R is our usage, our mem value. So this is our memory per core or per process, same idea, per process, per CPU for the job. So, and then the line right beneath that, -M, without going into too much detail, this value should always equal your mem value. That's the easiest way to kind of explain it to everybody and to make sure that there's no issues, is whatever your mem value equals, that should be your -M value. So what this job is saying here is saying we're requesting 1 core per node, and I want to use 2.5 gigs roughly with that 1 core. And then down here, the last two, -O, -E. -O is your output, and -E is your -E is also your error output. So if you put the -E, that's going to send the errors, if there are any, to this specific file. I think if you omit and you don't put the -E, all the output, errors and successful output goes to the standard out. That's just a way to kind of keep things clean. And then these %Js right here, these are variables now inside of LSF. So the $sign was a variable inside of Linux, and now we're using variables inside of variables, which is this will be the variable for your job ID. So whenever you submit the job, your job will get an ID, and this gets replaced with that. Down here, the optional specifications, we have -P, which is probably the most important of the optional specifications. This is the billing account that you want to charge. So in this case, if you don't specify this, it's going to charge your default account. But sometimes you have maybe your default account is your personal account, and you want to charge the account that's related to your professor's research. So you'd replace this number with whatever allocation number that is. You get that allocation number from right here, running my project. So you run my project and then you get a number right here. So you can only charge accounts that are yours, that show up here. So if you guys tried to put this number in, you'd get a message saying you don't have access to charge this account. So if the account number is not here, it's not going to work for you. To get the account number here, you have to have your CPU does equal core. Yes, sorry about that. Didn't see that just till right now. CPU and core interchangeable, even process to an extent. Same idea. And remember, there's 20 cores on Ada. But like I was saying about the account numbers, if you need to add an allocation, you either have to have your professor specify that on the application when he submits it. If he does not do that, then he has to email us and say, can you please add so-and-so to my startup account? And we can do it for him. But he can do it, they can do it themselves on the application that they submit to us. If they forget to do it, tell them to email us. And then up here, I kind of skipped over this a little bit, but this little diagram in the corner kind of shows the resources that this job is requesting. So it's requesting 1 core on 1 node. So imagine this as being 1 node on Ada, and we're just requesting 1 core. So we're requesting a very, very small amount of space here. And then 2.5 gigs roughly, which is not even 2.5 gigs, but it's a very small job, this example here. After the job specifications, after all these B sub directives, we have the commands that we're gonna we type in to load to load the environment and then to execute the job. So in this case, we're saying module load Python. It's loading the specific version of Python 3.5.2 built with the Intel 2017A compiler toolchain, and then we run the program right here. We have a couple questions. What's the difference between R usage memory and -M for memory? The difference is the -M is the enforceable per process limit, and then it's a long story. It's a long story. So we should always just keep these the exact same. Basically, one is saying this is how much memory I want to use, and then the other one is saying this is how much memory I'm allowed to use. So as long as we keep them the same, we never have an issue. If you Google the LSF, I think our wiki page even talks about it a little bit. If you go to our wiki and go to building your job stuff, let me show you that real quick. I'll show you after we finish here. And how is SU usage calculated? SU usage is calculated with the 3 factors I talked about. So wall time, how many cores, and then how much memory you're using. I believe on Ada, it's 1 SU is equal to 1 CPU hour or 2.5 gigs. I think it's 2.5 gigs. So there's the actual formula is on our website, on our wiki, that you can look at, but it's kind of easiest to imagine it as how many CPUs and how many hours am I using. So in this case, it says over here, this would charge us 2 because we're running 1 core for 2 hours and then 2.5 gigs. So basically cores per hour with memory factored in there. So the more memory requests, it's gonna your SU usage is gonna shoot up as well. So after you've got all your B-sub stuff, you put the commands that you're gonna run as if you would have typed them into the terminal. You just put them right after the B-sub stuff. And then your job, the LSF, when you submit this, LSF will look at all these parameters, start to set aside these resources for you, create whatever environment you had, and then it's gonna enter these commands as if you type them into the computer, right into the terminal. And then it'll send the output to wherever you put it, wherever you submitted from. Check your SU balance. We talked about this already. So you could list your SU balance with my project. This shows you all the accounts. So if you have more than 1 account, this is what it'll look like. This is from fiscal year 19. Yeah, that's what that looks like. And then to specify project account in the job file, it's that optional specification we showed, the -P with the account number. Also, you can change your default account, which is the account that gets charged when you don't specify an account number in your job file, with the -D my project minus D. I've only got one, so it's my default by default. But if you have more than one, you can just say my project minus D and then copy this account number or whatever account number in, and that account will get charged. So we're kind of running out of time here, but we're gonna continue, and then I'll stay around for questions if anybody has questions afterwards. Mapping jobs to cores on Ada. So in this case, we have a B sub minus N of 20 and a P tile of 20. So we're saying 20 cores per node. 20 divided by 20 gives us 1, so we're using one entire node. In example B over here, we have 20 cores on 2 compute nodes. We're saying minus N 20, P tile of 10. So 20 divided by 10 gives us 2, and this is what that would look like. We've got 10 on 10 on one node, 10 on the other. And then the last example over here, we've got 20 cores on 4, so we're saying minus N of 20, and then a P tile of 5 divides it up in that way. So why would you divide your job up? You typically divide your job up in case it might make your job run faster, because in this case, you're reserving the entire node. Over here, you're reserving only half a node. The issues that come then are these nodes of these cores on this node, other people can be running there. So you're running the risk of their job interfering with yours. Doesn't happen too often, but it is a possibility. It is typically faster for your job to run if you break it up like this, because like I said, reserving an entire node can take a little while if Ada is really busy. But the more you break it up, the faster it'll probably be able to run. These are some important job parameters. The minus L sets the job environment, the time. We talked about these already. And then job submission and tracking. So to submit your file, your job file, you put all those B sub parameters into a text file, like I said, and then you run B sub, and then you run B sub with a little arrow. So kind of what you're saying is you're saying, B sub, I want to submit this job file. You're actually redirecting some input, but that's like Linux technical stuff. You call it just like this, and this submits your job file to B sub, which is kind of the alias for LSF. Once you do that, you're going to see some output, which I think we're going to show you on these next couple slides. Once your job is submitted, you can use B jobs to list job information. If you say B jobs and then minus U, it's going to show you your job. So let me clear my screen and say B jobs minus U, Dylan. And this gives me all the jobs for me. Or if I say B jobs, I say B jobs and yeah, so B jobs minus U shows you your jobs or any other user's job. If you have a job that you want to kill, you run B jobs, it'll show you your job ID, and then you could say B kill to kill that job. And then these other ones right here, B hist shows you histories, information for a job while it's running. It's basically the history command, like show me all the previous jobs. And then LNU, which is for list node utilization, which shows you more detailed resource usage. So how many, how many cores did you use, how much memory, that sort of thing. Those are useful, but they're really dense to kind of go over right now. Job submission, insufficient SUs. If you submit a job, so here we're saying B sub, submit my job, and you don't have enough SUs, this is the error you get. Your account does not have it does not have sufficient balance to submit your job. So what do you do? Like I said, you ask your PI to transfer SUs to your account. They would have had to have had a startup account already, or you apply for more SUs if you are eligible. If you're a student, you have to go through your PI. The only ones who are eligible are most faculty members, actually all faculty members, then some other staff members at the university. But if you're a student like me, or like a grad student, you'll have to go through your advisor, your PI, whoever's sponsoring you. Okay, and then the last pop quiz. How much total memory is requested for this job? So I'll walk you through it. So we've got 10. Oh, this is kind of a trick question here. We're saying 10 cores, 10 p tile, a p tile of 10, and then a memory per core of 2,500, and this is in megabytes. So to calculate this, we'd go 2,500 times 10, which gives us 25 gigabytes, roughly. 1 gigabyte's not really 1,000, but we'll pretend it is. So the total kind of trips you up here. So in this case, the total memory is the same as the memory per node. Yeah, you just multiply 2,500 by 10, and that gives you the memory per node, which equals the total memory in this case. But on other jobs, that might not always be the case. But the answer is 25 gigs. I got it. In this example is only using one node. So that's why I said it's kind of, this actually should be worded how much memory is used per node. Because so here we see 10 cores divided by 10 cores per node gives us one node. So then 2,500 times 10 gives us 25,000, which is 25 gigs roughly. Same deal. Memory requests. So this is the last thing we'll talk about before I start taking questions and stuff. The majority of nodes have 64 gigabytes of memory, but only of that 64 gigabytes, only about 54 gigabytes is usable. 10 gigabytes is used by the system, so operating system, and then LSF needs memory to run and stuff. So if you're using all 20 cores, the highest value that you want to specify in your mem, so your -m and your R usage mem value is going to be 2,700 megabytes. That's going to put you right at the 54 gigabyte value, which is kind of dangerous still, but you could probably get away with it. The default value is, I think, 2.5 gigs. 2.5 gigs per job, not per core. But this is the default limit. This is probably the limit that you'd want to stick to if you're using the entire node. If you need more memory, then that's available. You can request a higher mem value, and you're going to be put into the 256 gigabyte queue, of which there are far fewer nodes. So your job might be there for a longer time. If you need even more memory, then you could use the extra large queue, which is a ridiculous amount of memory, terabytes of memory. And these nodes have 40 cores per node. So the old 20 core job limit goes away, and now you got 40. That's pretty much it. I think these next ones were, that was talking about large terabyte stuff. This is how you submit. We talked about it, B sub, and then the little arrow, like you're gonna put pointing to B sub, and then B job shows you what is running. Question from Trevor was, how do we sign up for the data management class? Yes, that link right there takes you to the primers pop-up page on our website. I'm not sure if the registration link is there. It should be there for next week, but you go there and you sign up. And then you'll get an email next week with these Zoom coordinates here. So that's pretty much all I got for Ada today. Does anybody have any specific questions about Ada that I can help you out with? So we do these pop-ups. We've been doing them every Wednesday. We typically start at 10 o'clock. We experimented with doing 2 in one day. Still trying to work out those kinks because doing them back to back is kind of really hard. We need some buffer time between them. But as far as I know, we'll be here every Wednesday, either me or another student or someone more knowledgeable than I on whatever topic. But you guys can go to that website and sign up there. Appreciate you guys coming out. And if you have any questions, just let me know. I'll stick around for another 5 minutes or so. Oh, that link doesn't work? Okay, let me get you a link. Mem equals to means, that means per core. So all specifications on Ada are per core. That's the main difference between specifying memory on Ada and Terra. Terra, you specify per node. So you say, like, I want to use 20 gigs of memory on this node, and then the system divides that up. On Ada, you specify per core, and then it multiplies it up. There is the direct link for that. A certificate for this course. As of right now, we don't have certificates for primer courses. We only had those for the like full length short courses, from which these slides are adapted from. It's just the short courses are about 2.5 hours in length, and the primers are obviously an hour, but with me talking, they go for like an hour, 10 minutes. So we don't do, as of right now, we don't do certificates for primers, no, sorry. Maybe in the future if I get to sign them. Interesting. Okay, yeah, it looks like you have to edit your previous response. So I believe it's the same form that we use. Back to the quiz question. The total memory is memory per node. Let's find it. Pop quiz, this one. No. So the total memory is memory per node. So like I said, on Ada, this is always going to specify memory per core. So the way we were able to find out memory per node, to find memory per node, you multiply mem, this value right here, mem equals whatever, by your p-tau value. Because your p-tau specifies memory per core, or sorry, your p-tau value specifies cores per node, and then your mem value specifies memory per core. So multiplying these two values gives you memory per node. In our case, in this one specific case here, the p-tau value is equal to our total core value. So the total memory and the total memory per node happen to be the same. That was sort of the discrepancy that I was pointing out that should have, that gets kind of confusing. But on Ada, these values always specify per core. So to find out per node, you multiply p-tau by your mem. It's possible to show how to submit the job in any cluster. You have to submit the jobs from the cluster, like you have to log into the cluster to submit the jobs. Unless you use there's a job composer on our, let's see, what is this? On the portal, let's see. So in this case, I'm gonna go to the Ada portal. And where is it? Jobs, job composer. So you can go over here. This is at the very top, the portal, jobs, job composer. Takes you to this thing, and you can build your job here. I don't have very much experience using the job composer. Whenever I've submitted stuff, I just write a text file. Actually, the easiest way to do it is people go to they go to our wiki. So if you go to Ada wiki, and then you go to building job files, and you kind of scroll down, there's some examples. You could just take these, copy it, and then put it in a example job, and you put this here, and then you save it. And now you have the file right here. So that's typically the easiest way, and you just have to remember that there's two different job schedulers. So on Ada, we use bsub, like so, to submit your job, just like that, bsub, and then you submit it. And then on Terra, we say sbatch. So I'm on Ada right now. If I try to call the Terra job scheduler, it just doesn't know what the heck I'm talking about. It just says, I don't know what that is, command not found. Likewise, if I was on Terra, Terra doesn't know what Ada is. But the easiest way to do it is go to our wiki and pull the example jobs and then modify them. That's how I would do it at the start. And I think that's by far the most common way, because we see these comments in people's jobs all the time. these same comments right here. So yeah, unfortunately, there's just no way like from one cluster to submit to all of the clusters. That'd be cool. I think that's the premise of cloud bursting, kind of. Well, not really, but no problem. Any other questions? Who's still here? No problem. I will see you guys next week. If you go to the data management course, I'll be there. Guys, have a good Wednesday. No problem. Yeah, the wiki is full of good information. Full of good information. Okay, I'm going to end this meeting. So if there's any other questions, send us an email, help@hprc.tamway.edu. That's where we're most responsive. You can catch us over there. But thank you guys for coming. I'm going to end this so the cloud recording is not too large. And yeah, you guys have a great Wednesday.